Chapter 11, number 41. A child exerts a tangential 53.4 Newton force on the rim of a disc-shaped merry-go-round with a radius of 2.25 meters. If the merry-go-round starts at rest and acquires an angular speed of 0.125 revs per second in 3.50 seconds, what is its mass? So we're trying to connect tangential forces, right? Connect tangential force to the mass, and it's clearly going to involve angular speeds, but really what we're saying is we know that we can connect torques to angular accelerations via, right, so connect the torque comes from the force and the angular acceleration, producing angular acceleration and the moment of inertia, which depends on the mass but other stuff. So let's have our picture as usual, and we'll say the child is pushing with some force F, the radius of the wheel being, let's say, capital R, and its mass being m, and this produces, we say, a angular acceleration, alpha, so as to eventually have a speed, omega, going around. All right, let's start connecting some of these things. Well, we know that, for instance, alpha is delta omega over delta t. And I have a delta t, and I have a final omega starting from rest, so I have delta omega. And so theoretically, I can get some numbers here, but I have them. So as far as I'm concerned, alpha is determined. And then let's talk about I. I is going to be, it's a disk, which means that it's a solid object. So I is going to be 1/2 mr squared. And then sort of, maybe not finally, but next, we know that the torque produced by a force is going to be the force times the distance. In this case, because the line of action of the force produces this as the vertical distance, which is just the radius of the disk. So putting all that stuff back into this equation, we end up with F times R equals 1/2 mr squared times delta omega over delta t. And then we can just solve for m. So we can do a couple of things. We can say one of the r's cancels out, and then we manipulate our things by, say, multiplying everybody by 2 and dividing everybody by r and so on, and we end up with that m will be 2f delta t over r delta omega, or 2 times the 53.4 newtons times the 3.50 seconds over 2.29 meters times, we end with a speed of 125 revs per second, which is unfortunate because we don't want that. We want radians, but that's okay because every revolution is 2 pi radians. And now we have numbers we can just throw into a calculator. And we get 207.8 kilograms. We seem to have 3 digits of accuracy, so this really becomes 208 kilograms.